If you remember your study of surface area, you'll recall that it has a formula that looks like this. We take the differential area that we cover and we integrate it from A to B. And if you remember, it's like a Pythagorean theorem where we'd say 1 plus the square of the derivative at the point square root. So it's really like 1 squared plus that squared, because you're creating on a curve, you're creating kind of a differential triangle. Think of that as like rise over run. And you integrate that from each piece from A to B. So you're integrating those very small triangles over the curve, and you're riding along the hypotenuse of each one. And as they shrink, you have the limiting process, etc., etc. You can recover the length of the curve. We have an analogous design, I suppose, for studying surfaces when we're looking in 3D space instead of just 2D space with surface area. Well, I'll say this. Technically, a surface is actually, in our particular case, is just a two-dimensional object, even though we plot it in 3D space. But let's not get hung up on details right now. So instead of defining those small little triangles and going across the hypotenuse, what we're going to do is we're going to take a grid on the surface, and we're going to take random points inside each of those little grid blocks, and we're going to construct tangent planes. So, as you recall, we've learned how to construct tangent planes at a given point for a surface defined by a function. And if we get those tangent planes, they're kind of like, I think of it almost like little armor pieces, think like an armadillo. Those little pieces are small little rectangles, and if you sum up those rectangles, they kind of approximate the surface area of the surface. But as those rectangles get smaller, but there's more of them, it kind of looks more like a tiled floor, and more and more and more and more, and eventually it smooths out, and the sum of those rectangular areas gets you the actual surface area. So if we have some sort of surface that can be described like this, z equals f of xy, then we can approximate that by summing the areas of the tangent planes along a grid of points on the surface. So basically we would create a bunch of tangent planes for all these little regions and sum them up. And then of course, if we took more points and did more tangent plane sums, those would start converging to the surface, or to the surface area. So we can say that the actual surface area is approximately the sum of these little differential surface areas, so the areas of the tangent plane. But if we were to think about what the area of the tangent plane is, and we took the tangent planes, if we take the definition of the tangent plane and we get that by kind of like using the gradient, and if we are construct vectors in certain ways, and there'll be an explanation in the next video about how we get there, what we end up with is something that is the way that this area is constructed. And it's 1 plus the square of the partial derivative with respect to x plus the square of the partial derivative with respect to y. And again, these are xy, xi, yi, so these are at these points. So at those points times the differential area there. So what you have here is something that looks a whole lot like this, right? And what we find is that the actual surface area, when we get into integral form, falls into this definition. We integrate over the region. So this is a double integral. This is not an iterated integral yet. Of the square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared. So notice that it looks a lot like this. So instead of this is kind of like a partial with respect to x, but there's not multiple variables, so it's just the derivative with respect to x squared, but there's no y term. But notice how very, very similar these are, and that's because they fundamentally operate very similarly in that we define some sort of geometric object. It was a triangle in this case, and it's going to be, I think, more like a parallelogram as opposed to a rectangle here. we're going to find the area, get the area of a parallelogram, and then we're going to sum all of those up, and that's going to give us our surface. And again, we're going to discuss more in the next video about how we get there, where this comes from, and why we can do this.